with the company, a little bit packaging.
Yes.
So I also invite, for example, Arshit to talk a little bit, Lorenzo, Davide, welcome back, and also other potential people, and the stage is yours.
Yes. Thanks for this very nice introduction. For me, it's always a pleasure to be back in Trieste. So today we talk about the principle of complementary energy with a spline-based stress function. This is some work that developed actually out of the topic of quantum computing, which I'm interested in. However, for this target audience here, I think it was a little bit more appropriate to speak about this component in the sense of a numerical scheme for solid mechanics. So if I still have time or there are questions, I will also at the end can explain where the motivation is in quantum computing for this topic. But I think it's also a self-contained topic as a numerical scheme. So since there are only a few phases left that I still know, I wanted to start also with a short personal introduction. So I did my PhD in Aachen in computational engineering science, and 2018 it was that I visited Switzerland for the first time, and I still have like a sticker here on my bottle, and you see it's quite some time ago. But still, yeah, as I said, I enjoy returning to Trieste, especially to Switzerland. Then later, so I moved from Aachen to Vienna, and since 2021, I'm a postdoc now at the Institute of Lightweight Design and Structural Biomechanics at Wien. My research interests include space-time finite elements, modular reduction, numerical design optimization, and quantum computing. And today's topic basically is located in the last two, where we'll focus, as I already mentioned, on the perspective of a numerical scheme, mostly here. Okay, so the content, maybe just for the time, is it like 30 to 40 minutes? Or, okay. Yeah, otherwise we just have to stop. No. So the content that I planned to discuss is as follows. First, I would like to discuss the theoretical basis. I don't know how many people are familiar with this principle, which is the principle of complementary energy. You may be more familiar with the principle of minimum potential energy, which is more popular or more common, I would say. Here we go into the different route. And based on that, I will present our work on the spline-based stress function. And you will see why this is a good choice. I hope that I will be able to convince you. And finally, I will present results for two problems that we detected so far. Okay, so that's the overview. Let's get started. So in solid mechanics, you have a very general variation of principle, which is the Wolbeke-Huvadiso principle. And this is a three-field variation of principle. And you later see why it contains three fields, but basically the message, okay, we have this variation of this term, which has different contributions. And yeah, if you solve for the stationarity condition, then you get the solution for both fields. So what are these different terms? So the first one is the total strain energy, which can be calculated from the strain epsilon ij. Then P is the potential energy of prescribed loads, calculated by the displacements of a body, Ui. And finally, the third term is the V, the so-called dislocation potential, which is represented by the stress sigma ij. And now you already see what is called the three-field variation principle, because it has these three independent fields for the strains, epsilon ij, displacement Ui, and for the stresses, sigma ij. And this can be used to determine all the fields, for example, from elasticity. So that's a starting point. Then, for the example of linear elasticity, it looks like that. So basically, I just plugged in now corresponding expressions for the different contributions and color-coded those. also take into account corresponding boundary conditions. And this condition that the variation of this term here is 0 or should be 0, then yields the following three things. So first, it yields equilibrium. So if you look at this term with the variation with respect to the displacement, then basically you see you have this term and this body force term and also the traction. So this is something that looks like the static equilibrium of the body. Second, if you it also yields compatibility. So if you take the variation with respect to the stresses, basically it's this term that remains, and this just say what you often have as a that you assume as a relation that the strains are talking derivatives of the displacement, and also here we have also the boundary conditions in displacement down. And lastly, it also yields this constitutive law. So if you take the variation with respect to the strains, basically this is what remains, and also this term. So basically this relates the stresses to strains via this stiffness tensor CIJ. And in this case. Okay. This is the most general setting, I would say, but you can also now see this as a generalization and look at more specific scenarios. So first one is the principle of stationary potential energy, maybe the one that is most known. And then second, you can also derive the principle of stationary complementary energy. For the principle of stationary potential energy, we just denote the potential energy by this pi. We say when we put to 0, we just have the terms from the previous slide as before, and we assume that it's constitutive law, so the relation between stress and strain that already holds, that also the strains are given to the displacement, so the derivatives such as displacement, and that the displacement boundary conditions are fulfilled. More technical assumption that or still basic assumption that we assume the existence of potential. Then you can end up with this principle, and this basically gives you the opportunity to compute the displacements based on your given material and for the boundary condition. The principle of stationary complementary energy is now a little bit different. So you keep other terms. Basically, the complementary energy is now denoted by this chi star, and it has some term in the stresses, where this tensor now is the compliance tensor. You have the contributions from the body force term, and your contributions from the boundary where you prescribe the displacement. And again, if you take the variation and set it to 0, you can use this later to compute the stresses. And the assumptions are that, again, this constitutive law holds that you have this equilibrium condition between the stress and the body force, and also that the traction boundary conditions are fulfilled. And again, as before, the existence of the traction. So basically, before I said, okay, this is a very general principle, and this you have three consequences. So the equilibrium, the constitutive law, and the compatibility. And basically, what you do now in this specific cases, you assume that some of them already hold. So, for example, here you assume that equilibrium is fulfilled, and the constitutive law holds, and then this just gives you like the last missing third relation. In this case, the compatibility. Okay. So before we start to look at more specific examples, maybe feel free to interrupt me at any time if there's something unclear. I would like to have it really in the interactive session. So,
this is regardless of the constitutive law.
So that it holds, yes, but the constitutive law enters now through this assumption here.
Yeah.
So I mean here it's a compatibility tensor, but this is basically the inverse of the stiffness tensor. So I assume that this already holds this way. Okay. I hope it will get a little bit more clear now, also looking at the like one step further, because so far we have the only condition was stationarity. Yeah? So we just set the variation to 0. But now we want to have like a minimum principle. So far stationarity is the first or the necessary condition for minimum. But now we're interested really in a minimum principle that provides the stress field sigma j of this elastic body omega, where we have some portion of the boundary where we prescribe the displacements you have, and some portion where we prescribe the tractions. And as before, we have this body force density of phi. Well, again, looking at the linear elastic solid, we have that then the internal complementary energy, which was basically the first integral, is given by 1/2 of the integral of the body. Yeah, it's combined tensor multiplied with stresses, which are our unknowns in this case. We also have external contributions. So one from this body force density, one prescribed displacements. And you may ask, okay, then we can define the total complementary energy. That's the sum of both contributions, so internal and external ones. And you may ask, okay, what is about this portion here? But this show up next. Because before we can state this minimum principle, we have to restrict ourselves to only statically admissible stress fields. So basically, we want to minimize this term here with respect to all the stress fields, which are our unknowns, but we are not allowed to take any stress field that minimizes this term, but these stress fields need to be statically admissible. What does it mean? Basically, these are the conditions, the assumptions that we've seen before. So first, the stress field needs to be in equilibrium with the body forces, and also the traction body conditions need to be equal. So that's the way how these body conditions enter into this principle. If we assume that we only restrict ourselves to these statically admissible stress fields, we can state the principle of minimum complementary energy. So we say the variation of the complementary energy is 0, the second order variation needs to be greater than 0, so that's the minimum. Then the principle can be stated as the total complementary potential is the minimum with respect to variations expressed when the system is in its full state of equilibrium. So in this way, we will use this principle to compute our stresses. But we have to restrict ourselves only on statically admissible stress. Then the structural analysis problem, formulated stress, can be written as, okay, we minimize this total complementary energy, which is now functional of the stress field, where all the stress fields are statically admissible, so denoted by this category S, where this function is just given through these two contributions, internal and external. Okay. I would like to make a quick comment on this sufficient condition for minimum, because this may not hold in general, but in case of linear elasticity, this condition is fulfilled when the lines tensor, so material behavior, which characterizes that, if that is positive definite. And if that is true, that is usually true, then this condition is also fulfilled, and we can use this minimum principle to compute our stresses. So that is the underlying idea. And just to give you a little bit of a context, because the most popular are displacement-based finite elements, and what are the relations, I would like to go to this visual way. So we have generally in linear elastostatics, we have the three fields, the stresses, the strains, and the displacements, and we're interested in one of them or all of them. And what we have as field equations are equilibrium, compatibility, constitutive form. So now we have two choices. So we can either go this path and follow this variation of principles that we just discussed, or we could also go the other way and apply field elimination. So, for example, replacing the strains by the displacements, but we will see this later. So for the variation principle, there's again different options. So this mixed formation, the most general one that I used at the beginning. Then we have the potential energy, which is formulated in terms of displacement, so we did not discuss, or the complementary energy formulated in stresses, which is what it is. So for the field elimination, you can take all these equations and, for example, eliminate strains and the displacement. So express everything in terms of stresses, and then end up with the so-called Beltrami-Michel equations. Or what is commonly done, so you eliminate the stresses to the constitutive law in terms of the strains, and then the strains to the derivatives of displacement, and you get the Maillard equation for the displacement. And then that's basically the type of equation where you also apply, for example, your calculation on, and you get them. Okay, but we follow this other part, yeah. So we didn't go here. So here actually there's also a way or equivalence between this and this, but good part today. But rather, okay, we follow now this path. We have this principle of minimum complementary energy. So now how can we use this to compute the stresses? And in particular, what's done already in literature is to use so-called stress functions. You see what it is more detail later, but basically this is some way to consider the static possibility automatically. And then once you have plugged in such a scalar stress function for the stresses, for the stress tensor, you can find elements for element methods, so stress-based elements, or you can apply analytical methods to solve for the stress function. And in this, okay, maybe I will go to the disadvantages first. So assume that we took this part, so we have up with the displacement-based element method. If you're now interested in the stress prediction, then usually this method, the lack of good stress accuracy will cause distribution. So we use a lot of elements. So the computational effort is quite high to get good accuracy in the stresses. When you look at the stress-based finite element method, then these elements are not so popular, I would say, for a reason, because you can derive those elements, but these elements have many degrees of freedom elements. So, for example, there are 20 degrees of freedom per element for solid mechanics, where in 2D, we would draw a triangle which has 6. Or for stress, even more. So, therefore, I think they're not so popular. Also, with the complication with the statically opposite stress fields. Yeah, okay. Analytical methods work, but of course, they're just working for some specific geometries or boundary conditions, so they have a lack of flexibility. And the approach that I will present today is a Spline-Based stress function, and so it's located here in this reason. So it uses the principle of minimum complementary energy and stress function approach. And as you can see, this is very efficient and yields accurate stress results. So that is for the context and the relation to other existing methods in literature. Okay, so let's start to have a look at this Spline-Based stress function. So starting point is this analysis problem that you've seen before. So we would like to minimize the total complementary energy as a function of stresses with respect to all static stress fields. And the question is how to handle this constraint. So imagine you have an optimizer, but this optimizer can only handle unconstrained problems, optimization problems, and you would have to somehow get rid of this this constraint of static stability, or formulate it slightly differently. So how to transform this constraint problem? This is the driving motivation for the approach. So just as a reminder, statically admissible stress field means you have equilibrium with body forces between the stress body force density, and we need to fulfill the traction boundary conditions on the part where we prescribe the tractions. In the following, I will neglect body force curve for simplicity, but it also works there was a closed loop. One way to handle this constraint is to use a penalty term. So, for example, you could introduce some penalty term IE. And okay, this doesn't make sense here. You can ignore this. But in the end, you could come up with an unconstrained problem where you minimize the total complementary energy, and you have this penalty term where this accounts for the equilibrium, and you have some penalty rate lambda. But as known in practice, like this can lead to some issues. So how to choose lambda in any penalty method is usually the question that nobody can answer. And also, depending on your approach, you would like to choose lambda as much as possible, but this can also lead to some scaling issues. Okay, so we are looking therefore for an alternative technique. We would not like to use this penalty term. And that's where this spline-based function comes into play. So the idea is to represent the stress tensor sigma ij to some stress function phi and some differential operator. So basically, you just want to find expressions for the different components of the stress tensor as derivatives of this general tensor value stress function. And this will yield, so you choose the f in a way that this equilibrium condition is ultimately filled. So there are still the traction boundary conditions that you need to obey, and this will translate into conditions for the stress function phi. So that's the general idea. Okay. And we will follow this idea for the two-dimensional case, and there exists for a very long time already the so-called Airy stress function. So this is a scalar stress function phi, which depends on two coordinates x and y, and the stress components then of the stress tensor are defined in the following way. So the sigma xs xx is the second order derivative of the scalar stress function phi with respect to the y coordinate. Sigma yy is the second order derivative of phi with respect to the x coordinate, and you have sigma xy is equal to this mixed derivative, second order derivative with a minus sign. And if you define the stress tensor components like that, you can observe that the equilibrium is automatically complete. So, oops, sorry. So, for example, if you consider the equilibrium in x direction, so you have the derivative of sigma xx with respect to x plus the derivative of sigma xy with respect to y, and you plug in these definitions here, then you get this equal to the third order derivative is x and theta is y minus the same term, so this identically equal to 0. Okay, so by choosing this definition, we get equilibrium condition automatically. So now, what is our contribution? Our contribution is now to represent this scalar stress function through a novel spline-based approach. We will see later why this is well suited for it. So I don't know how familiar you are with these splines, so that's the reason why I would like to use it quickly. So in general, this usually it's used to represent geometries. So for example, this could be a parametric surface, so with two parametric coordinates, psi and eta, and this could be like, for example, it's embedding in three-dimensional space, it could be a three-dimensional position vector. And then you have the sum for each parametric direction, one set of polynomial basis functions in the psi direction and the second parametric eta direction, and you multiply this basis function with these Bij, which are the geometry representations of the control points. So these are coordinates. And then you can you just go over this parametric dimensions and you get the coordinates of this surface. So, and you see that this has some structure, so that runs from I with 1 to m and j is 1 to m. And therefore, these control points, they can be also looked at this control net. So each of the red dots is now one control point, and we define them to represent the surface, which okay, we have the control points. And yeah, each of the control points will use ij corresponds to basis functions ni and mj. And then you get the surface out of this like this. Yeah. And for this here you have so-called mesh, which are the so-called knot vectors. So in both parametric dimensions, we have these basically these knots which define mesh. So I think it's better to understand it with this specific example here. So if we have a knot vector in the xy direction, which is here basically 0, 0.51, so that will be that direction, yeah. So the xy coordinate will run like this for different values for eta. You will always run from 0 to 1 like 1. And for eta, we just have one element, so to say, we have only 0 and 1. So this is in this direction. So those are the two parametric problems. So this also under basic working principle for geometric analysis, where you will define the geometry to this, but also your unknown physical fields, for example, like the displacements. You can do this. And we will use it actually for our stress function. So what are the different components? So first we have this spline-based stress function. I call now phi hat, which depends on these two parametric coordinates, psi and eta, roots of B-spline, and this is a scalar function. Yeah. And yeah, okay, you can define this in physical coordinates, where you actually have your problem, but you can also define it with this hat in the parametric coordinate. Then I just use the expression as before. With the difference that now, instead of the control points, I have now here scalar valued control values finite j. But they define the stress function in the entire domain. Then we will have a geometric mapping to get somehow from these parametric coordinates to the physical coordinates x and y. This can be any kind of mapping. It can be spline-based, but it doesn't have to be spline-based. Show today it has been spline-based. And yeah, maybe for notation. This NIP and MJQ, those are these polynomial basis functions between P and Q. And we have these control variables phi ij. And N and M are the number of basis functions for control variables per dimension. That's something we can choose. Okay. What are the features of this approach? Why it is so advantageous for application? First of all, we can choose the degrees of the basis function as high as 1. So we can always ensure that we have continuous second order derivatives, so which means we have continuous stress function. This is in contrast to using displacement-based finite element, where you only have stress continuous inside an element, but not continuity across elements. Then the derivatives of the B-splines are B-splines again. And these derivatives are connected to their control variables. So they are not completely independent. And I've already shown in the beginning that using this area stress function in this way, we fulfill equilibrium, but we are still a traction boundary condition. And we need some way to prescribe or to ensure that the traction boundary conditions are fulfilled to also integrate this in our answer. And as you remember, the stress components will traction are second order derivatives of those spline-based stress functions. And we will relate the second order derivatives later to the spline to the stress function itself through this feature of this splines that these splines are again spline and contact. Yes, just a bit here again. So traction boundary conditions of conditions for second order derivatives of the stress function result in a system of equations, and finally for a subset of these control values phi j, where we solve for them, we already have fulfilled the traction boundary conditions. Okay, how does it look for the traction boundary condition? So tractions are in a product between stress tensors are normal. on this part of the practice stresses, and here for the components already plugged in the definition of the area stretch function. And if we want to prescribe some of those values here, we get a condition for the second order derivatives, and using this mapping we can express the second order derivatives as phi with respect to the physical coordinates as combination of terms depending on the second order derivatives of the stress function with respect to the parametric coordinates. So our interpolation functions, they will define with respect to parametric coordinates. So therefore we could not evaluate directly this, but we have to go basically apply a chain rule and we get something like this. So now from conditions for these second order derivatives, we get conditions for these second order derivatives and also for first order derivatives. And finally, since our spline-based stress function, so our phi hat is expressed in these previously defined basis functions, so we cannot be talking about that. So the conditions for this, the only degree supreme that we have are those control variables. So conditions for these terms here lead to conditions for the control variables. So, and all of that is for the traction bound condition. So the second component is static admissibility, because equilibrium is fulfilled by definition of defining stress tensor like this. Okay, I will show you a simple example for the case where we have no mapping. So the mapping is actually the identity. So assume, so this in this case this is just the unit square. So assume you want to prescribe the normal stress here sigma y in this case. Then the control net for the second order derivative of the spline would look like this for a specific case. And in this case, we can just interchangeably use x and xi because the mapping is the identity. So describing this stress tensor component here would lead to conditions for those control variables that define the value of the stress function on the boundary. And now, as I mentioned before, the control variables here, these spline, are related to the control variables of the first order derivative. And basically, or essentially, a condition. So if you prescribe here one value, let's say 2, then this leads to a condition for those three values. Yeah. You can also imagine if that was, if you would do some observation of the derivative from here to here, and you have two values here, you just spread up, you get one value here of the derivative. So we propagate in this direction these values that we prescribe in the boundary conditions, and we can do this one more time. And basically, so from these two conditions, all the control variables for the actual spline, so no derivatives are already prescribed. And you can also do this for all the other components if they are part of some boundary conditions. And you could end up in a situation where most of these control variables are already defined with the boundary conditions. And in this case, only this central control variable here is not yet determined. Everything else is already determined through the boundary condition. So later also, the missing step is to use this principle of minimum complementary energy to compute this last unknown control variable. Okay. Okay. So that was a very simple case where we have the identity mapping, where we want to compute the stress not only in the unit square, but also some more general conditions. So therefore, it also works in general settings. So for example, you would like to minimize pointwise difference between the fractions, which are nodes in this case, and some prescribed fractions. You can just try to minimize this integral where you have the square differences. You can also think of a case where you do not know pointwise the stress is a force distribution, but just the resulting force. You can also apply that as a boundary condition by minimizing this residual between this fraction integrated over the boundary and some prescribed force F1. You minimize this. And you can do this by choosing, by applying the optimality conditions. So So here in our traction, the stresses are hidden, and through our stresses, our stress functions. So our control variables. So you can just take the derivative of this and set it to 0 to apply this minimization. So this is the general way how we apply boundary conditions for the stress function. Okay. So now we have equilibrium fulfilled. We have some way to prescribe the traction boundary conditions so that ensures static admissibility, and by that transform this constraint problem into an unconstrained one. So how does it look in practice? Yeah, so basically we first set up this spline-based stretch function phi hat, so we can choose the number of control variables, the degrees, so which means we can choose our discretization in some sense. And we have to define this geometric mapping, which maps the unit squares of the parametric domain to our actual geometry vectors. Then, next step, we can set up the system of equations for the traction boundary conditions and solve this to compute already a subset of control variables by this addition here that I explained before. So at this stage, all the boundary conditions already determine part of our unknowns, and we are only left with a few unknown control variables. Then the next step is to solve this stationarity condition, so in principle stationary complementary energy, or if we want also to minimize the complementary energy with respect to those remaining control variables that have not yet been determined, to compute our stress function phi hat. Once we know our stress function phi hat, we can evaluate the second order derivatives of that to get the stress. And we have the stress distribution in the entire program. So this is the outline of the approach. And as a remark, in this way, this constraint of static admissibility is automatically fulfilled through our answer. So we do not have to take any further action to ensure that. Are there any questions regarding this approach? Okay, if that's not the case, I'll finally show some results. Most interesting part, maybe. First, for bending beam by uniform transverse loading. So assume we have this beam, we have some uniform loading from the top, and we have some counteracting forces on the left and the right hand side. And the boundary you can just prescribe from that to use the boundary conditions for the top and bottom. And also for the left and right hand side, just in the way we showed before. And in this case, we use 3 basis functions in that direction, 6 basis functions in that direction, and quadratic functions here in that direction, big order in that direction. So in the end, we have 3 times 6 unknowns, so 18 unknowns. The control net in this case would like this, so we would only have 2 unknowns for determining the stress field. And yeah, loading was 1, and that is what you get. So this is the stress distribution inside the entire domain. Very smooth, very nice, with only 18 unknowns. You can also have this for the other components, but to really get an idea how accurate it is, we will compare to some analytic approach and some power series approach, where they just chose some polynomial, which was a choice that has come from previous trial and error. So not so clear how this should be in general with these coefficients. And we look at the stress distribution among over this line in the middle. This is our approach. This is the reference one. And we also can apply some simple beam theory. Very good agreement. It's not so interesting because it's basically linear. But this other components of the sigma yy is a bit more interesting. We again have good agreement with the reference, and this is something you could not model through simple beam theory, but because this would give you 0 for the component. Okay, I will skip this for not so interesting a component and go to another test case, which is already challenging, or it's still challenging for today's state-of-the-art method. And this is with more complex material behavior, so anisotropic material behavior. And we look at this bilayer cantilever, which basically has two parts with two materials, and these patterns here, they show like the anisotropy of the material. In this case, we use two patches. We divided this in two patches, and we have a total 168 unknowns. And this is the result that you get. So you see this discontinuity here in the stress, which has to be there because of the jump in material properties. For sigma YY and XY, you get still very smooth results. And comparing this with from some paper where they also use as a reference some 2D finite element simulation, displacement-based, you get very good agreement, and we compare the number of unknowns. In the reference, they use 1,600,000 unknowns. In our case, we have only 168, and we get very good agreement. So I don't want to make a big claim here because I don't know if that has to be fine like this. So I didn't do the reference myself. At least that is what they use as the reference. And so they did some mesh convergence study apparently and compare their beam model. But yeah, this is quite significant decrease in the number of unknowns. Also for the other components as work, and I think I don't have so much time left, therefore I want to show the last one, where material behavior is again isotropic, but now we have a little bit not a rectangular more, but a non-prismatic parabolic shape. Also, therefore, difficult to solve with analytic methods. In our case, we have 50 unknowns. Again, they have smooth stress distributions. And if you compare the results again here with what they validated their B model with the finite element method, very similar results. And again, 50 unknowns in our case, the reference 200,000 unknowns for the displacement-based finite element. Okay, so let me sum up. I showed you some way to use this principle of complementary energy to compute stress fields. We presented our work on the spline-based stress function approach, which is very useful in this application, where the static admissibility is fulfilled by design, and the spline properties allow for accurate and efficient solutions. And finally, I showed this validation for 2D test cases that are even challenging for today's state of the art. With that, I'm done. Thanks a lot.
It's very good. How do you do M and is it like the fire interval? Or you perform some convergence analysis like?
So how would you do it in classical methods? You would try, but you would try to keep it as small as possible.
Yeah.
So that would be the same answer. So I try to keep it as small as possible and see what I need for good accuracy. So we need at least like second order in the stress function to get constant stress values. And yeah, if you have some idea about how your stress distribution look like, it's the quadratic function. So you know, okay, I have to take fourth order. These are things you do. Thanks.
Is this just for linear elasticity or different constituted models?
So what I showed is for linear elasticity. The reason why I focus on that is because I would use this minimum principle, not the stationary principle. In my application, that has something to do with the quantum computing part. But if you just do if you just require first variation equal to 0, you don't need this. So that sense, I think, can also be applied to other or to other situations where still the second condition is also fulfilled.
Thanks a lot for the so if you go to the second test case, so the one with the B-level and river, in that sense, yeah. So there you have as you mentioned, the discontinuity in not because you have different materials.
Yes.
But then this is the sigma xx. So in principle, but the second let's say the second plot that you have there for the sigma xy probably, you remember? Okay, so now this is continuous. So let's say it doesn't change anything if you have continuous or discontinuous. So do you see differences in the approximation of the different subfields, let's say sigma x, sigma y, that let's say depending if it's continuous, discontinuous or not, let's say.
The nice thing is, I just sort for the stress function.
Okay.
So everything is just post-processing.
Okay.
So I just had one scalar stress function. I could plot it, but
okay, and
you
then
cannot interpret, and then I take the second order derivative.
Okay.
And yeah.
No, but see, so in the other cases, you always had sigma, the components for sigma, which were, let's say, even in post-processing, they were always continuous, no? So like in this case, instead at least this x-axis is discontinuous.
Yes.
So at least from the functional point of view, this is different. So do you have noticed some kind of accuracy difference in test cases if you have a different kind of regularity of the actual function that you are approximating?
So what I did here is that I mentioned only quickly, I have two patches. So I have one stress function for the upper part and one here, and I couple them. So I do not do like one big rectangle because I have very smooth splines. I would probably be not so good in approximating this discontinuity.
Yeah.
But since I allow this discontinuity of the stress function, also the stress components can have discontinuity like this or not. So from that point.
So say that, for example, exploiting the same amount of number of bases, let's say the same setting for the approximation, if you consider different materials or the same setting but the same material, let's say, are there differences in the kind of decaying convergence with respect to the number of bases?
I wouldn't expect difference there because now basically I have also two.
Just use your sigma and then you just put stop it there.
Yeah. So I have the phi and now I have like the phi here. The phi here, they're basically independent except for the coupling conditions. But the coupling condition doesn't lead to any condition on the sigma xx. Therefore, it can also have the jump.
Okay. And I also have another curiosity. How is the quantum part? So where is the quantum part taking a place in that context?
Yeah, so I
will just read this.
Yeah, the big picture is I want to solve structural design optimization problems. So for example, minimum compliance of the structure. I have a very powerful optimizer, which is quantum annealing, which allows me to find the minimum of very complex cost functions efficiently. We developed some approach where you can formulate the minimum compliance problem together with the minimum complementary energy as one optimization problem. Solving that optimization problem will give you both the optimal design and the full stress field. And yeah, that's a reason why.
Okay, like, no, because you see, so in this case, what I also get from this is that you can, so instead of standard finite elements, you can really decrease the amount of unknowns because the visibility of the system not all to a very, very small dimension. So this is like a further, not optimization, but the reduction of the system to solve so that with quantum computing this is now treatable. Or can you do also the quantum part of the finite element? So
no, I wouldn't do that because this is our approach is tailored for the quantum computing with knowing mind that we have a powerful optimization tool.
Okay.
And it doesn't work with the finite element. So
but also because it's too big, right? So like in terms of the capability of the quantum computer.
Yeah.
So this will also complex.
But still, this would be too big for current.
Even 160, yeah, sure. No, I feel let's say 1 million is too big.
Yeah, but as I said, so therefore I also presented in that way today. I think even if you forget about the quantum part, it's still very relevant and interesting as a numerical scheme as it is to get high accuracy stress predictions with very little number.
No, yeah, that's my part. So you already have a huge reduction there with the same accuracy, and you're getting the plus the factor regularity for the stress function, which is something that you always want that. And my question was that because the very first project we did, I was doing this kind of buffering analysis for that system, And I was also having this stress function phi, and essentially every time that I was looking at this continuity material change in the parameter, then I was looking at different convergence of the displacement and the stress field. The stress field were actually always bad, so that's all. But yeah, that's all.
Thank you.
So let's take again Fabian is here is a video.
But I'm staying in 402, so